Hi guys, my name is Hannah Hashimoto. I am a second year biochem major and I am working with Taylor Witter, who is also a second year biochem major. Today we are going to be looking at chapter 17.2, problem number 6. And in this problem, it is asking us to find the overall reaction of a voltaic cell along with the standard cell potential. It is also asking us to determine the cathode and anode along with the charges of them. And finally, it is asking us to find the cell potential at non-standard conditions. So, in part A, we are asked to find the overall reaction. For this voltaic cell, we know that the left side of the cell notation is going to be oxidized, while the right side is going to be reduced. So we can start out by writing both of these in the reduction form. So it will be Cr3 plus 3 electrons, turning into a chromium solid with a reduction cell potential of negative 0.74 volts. And we will have iron 2 plus with 2 electrons, changing into iron solid. And that reduction potential is going to be negative 0.44 volts. So since chromium is actually being oxidized, we are going to flip the equation so that chromium solid turns into chromium 3 plus and 3 electrons. And since we flipped the equation, we will now flip the reduction potential into an oxidation potential. So that should be positive 0.74 volts. And now we will use these two equations to have our overall reaction. We see that there's 2 electrons from iron and 3 from chromium. So we need to multiply the top equation by 3 and the bottom equation by 2 to balance out the electrons. So on the left side of the equation, we should have 3 iron 2 plus 6 electrons and 2 chromium solid. That should turn into 3 iron solid plus 2 chromium 3 plus, and of course our 6 electrons. We can cancel out the electrons and come up with our overall reaction of 3 iron 2 plus, which we know is aqueous, and 2 chromium solid, turning into 3 iron solid and 2 chromium 3 plus, which is aqueous. And this is our overall reaction. In part B, we are asked to find the standard cell potential. So written out, we have our oxidation potential and our reduction potential. And we know that E cell naught is equal to the reduction potential plus the oxidation potential. So we can simply plug those in. The reduction potential is 0.44 volts, while the oxidation potential is 0.74 volts. And we calculate that out to positive 0.30 volts, and that is our E cell naught. In part C, we are asked to determine if the chromium electrode is the anode or cathode, and if it is on the positive or negative terminal of the voltaic cell. So we can look at the diagram and determine all of these answers. We can label what we know first. So we know that chromium solid is on the left with chromium 3 plus in solution and iron 2 plus in the solution on the right, with iron metal on the right. From earlier, we determined that 0.30 volts should be read on the voltmeter. Of course, we can't forget our salt bridge. The electrons should be flowing to the right. So, as we determined earlier, the left side was where oxidation occurred, and the right side was where the reduction occurred. And oxidation contains the anode, while reduction contains the cathode. And since this is a voltaic cell, we know that the anode is negatively charged and the cathode is positively charged. So from this diagram, we can determine that the chromium electrode is on the anode side, and it has the negative charge, or the negative terminal end of the voltaic cell. Finally, in Part D, we are asked to find the cell potential under non-standard conditions, which are given to us. So we can use our equation to find E cell equals E cell naught minus RT over NF natural log of Q. So we know that E cell is equal to positive 0.30 volts, which we determined earlier. R, which is the gas constant we are going to be using, is 8.314 joules per Kelvin mole. We can assume that this is under room temperature, which is 298 Kelvin. N is the number of moles in the overall reaction, which we determined earlier to be 6 electrons. F, Faraday's constant, is going to be, as always, 96,485, and that is going to be in coulombs per mole. And Q is going to be our products over reactants. So our product was Cr3+, and our reactant was Fe2+, but we can't forget the coefficients. So chromium had a coefficient of 2, and iron had one of 3. And since we know those concentrations, we can plug them in as 0.01 squared over 1.5 cubed. So now that we know all of those, we can simply plug it into our equation. So E cell equals 0.3 volts minus R, which is 8.314 joules per Kelvin mole, times 298 Kelvin, all over the 6 electrons times 96,485 coulombs per mole. And that is going to be multiplied by the natural log of 0.01 squared over 1.5 cubed. When we calculate this out, we get that E cell is equal to 0.32 volts. And we can cancel out all of our units. Moles, moles, Kelvin, Kelvin, and then joules per coulombs are left, but that is the same thing as volts, so we're all good with units, and this is our final answer.